Welcome Mechanics of Materials students. In this lecture we'll be discussing stress concentrators. So these are features in real materials that basically make your local state of stress significantly greater than the average or nominal stress that you think you've applied to your part. And we're going to be using a simple example of a hole drilled through a bar to demonstrate this concept. These have significant design implications in that, as you can probably guess, you're going to design your parts, choose your materials such that your applied stresses are below yield or below a failure criteria of some kind, or such that your strains lead to acceptable deflections. If all of a sudden there's some feature, some characteristic of your material that makes a local stress state significantly greater, that's something you need to account for in your design, either by going with something that's stronger, something that has a higher modulus, better fracture toughness, or by reducing the nominal load, or best yet, get rid of the stress concentrator when you can. Okay, what causes stress concentration? Abrupt changes in geometry. So we'll try to use this. I'm going to blow this up a little bit here. If you think about stress in a part as being like a vector field, if we're up here, we've got this sort of rectangular bar, and we're yanking on the ends, and it's W. It's a width W wide and T deep. On our X and Y axis, we're pulling on it in the Z. If we're away from the end, something we'll get into in a minute or two, we have a uniform stress state, generally speaking. If the material's homogeneous, the stress at this point here and at this point here and at that point there, we can expect it to be about the same. Okay, so say someone drills a hole through the material, right all the way through. Well, we're applying the same force, and so if we look at a plane cut through the material, right here at the edge, a point here, it doesn't have anything to support itself right adjacent to itself. It is a hole. So the stress state right next to this defect is going to be much higher. And if we put a little volume of material next to this hole in static equilibrium, and we looked at how hard, say, we had to tug on this piece of material versus the one adjacent to it, we'd see that to keep this from moving, we have to have a significantly higher force on a differential piece of material than we do next to it. And so we would have a decreasing stress as we got further away from that hole. But right near the hole, our stress state is extremely high. And in fact, it's higher by a factor of about 3 in the case of a smooth hole with a diameter that's significantly smaller than say, our smallest diameter of our part. This will hold true for a sharp corner. There's a high stress state at that sharp corner. Any kind of section reduction or increase, again, simply because we have a discontinuity. If we have the axis of a part here, even if we're getting bigger, if we're transitioning dimensions, we're going to end up concentrating stress simply because we have a change in our geometry with respect to the direction of applied stress. The sharper the discontinuity, the higher the stress concentrator, regardless of the actual section thickness change. So we're not going to get way into stress concentrators in this class, but we do need to know they exist, and we're going to implement them just a little bit in designs and just show how different our applied stresses have to be to keep our actual max stresses below whatever maximum criteria we establish. So I've just alluded very, very qualitatively to the origin of stress concentrators as being kind of a disruption in this vector field that we're using to represent our stress throughout the material, and causing a stress at a point to be much higher than at another point. Kind of now you know why you learn stress at a point rather than average stress. It isn't all the same. Let's look at how we get this ratio of max stress adjacent to a discontinuity, say, versus our average nominal stress. Most of the time, these factors are determined either empirically or they're determined theoretically with finite element and other elasticity calculations that are beyond the scope of this class. So we're going to use a few of them or look other ones up in handbooks. And in a lot of cases, that's what you'll do in practice, especially as you start into your career. So for instance, the stress concentrator for this through hole that we just looked at is denoted by a capital K subscript T, meaning K, which is a concentrator factor, and the subscript T means theoretical. It means somebody calculated it from elasticity theory. It wasn't measured with tests. And the way you use it is this equation right here. You take your nominal stress, which is our force, divided by the cross-sectional area W times T, and you multiply your stress concentrator by that, and that's the max stress you're actually going to get in the part. So if we say wanted to keep our max stress in a part below yield, or below yield times the safety factor, for instance, or any other value, we wouldn't use nominal stress as an input. We would use nominal stress times our KT. How big is KT? It's big. For a smooth through hole, that where the hole diameter is much less than the largest dimension of a part, it's 3. So say we're designing against yield, and we have a yield of 100 megapascals, for instance, and we wanted to be able to carry 40 megapascals. That's less than half of yield. We have more than a 2 times safety factor against yield. Well, if somebody drilled a hole through our part, all of a sudden we have to multiply that nominal stress by 3. Now the max stress in the part is actually 120. So not only have we lost our entire safety factor, we probably yielded up against that hole, and that could cause all kinds of problems, not the least of which violating our design parameters. So, and 3 is probably on the small side compared to how a severe section thickness or a very sharp corner can change your max stress versus your nominal. Okay, so here's another little example. This is taken from a table in an older textbook where KTs are tabulated for a smooth bar with a groove. And in this case, the bar is 20 millimeters in diameter. We're assuming it's loaded in tension. Those, in addition to the the stress concentration factors varying with the shape and configuration of the defect, the discontinuity, it also varies with how we loaded it. For instance, for the same scenario, if instead of yanking on the bar, if we bent it in flexion, we'd have a different stress concentration factor. And if you can think about it, that's because our stress distribution in the part would be different to begin with. And so the interaction of the defect with that stress distribution would be different. So just like in cases of things like fatigue and other types of real material problems, a lot of the tabulated numbers you see will be specific to the material, to the geometry, and to the loading state or the stress state, the nominal stress state. So in this case, it's specific to a bar in tension, in uniaxial tension. So as it turns out, KT is dependent on the ratio of the reduced diameter, which in this case is 16 millimeters, to the original, but also to the radius of the groove. So we could have a really fat bar and we could reduce it a lot by milling in. And then if we had a really tiny radius groove, it would be more severe than if we milled in to the same, reduced the overall section by the same amount, but had a big wide radius. So basically, if we did something like that, real narrow groove, would be more severe than this wider one we see. So in the table, that's captured in the R versus D ratio. You look up on a table and it says, so what's your groove radius ratioed to your nominal diameter, and then what's your reduced diameter ratioed to your nominal diameter. And if you know those two and you know that the shaft is in tension, you can look up on a little chart and it says, okay, your KT is, in this case, is 2.6 for tension and for these two values. So handbooks will have those type of plots. They'll either be tables, that might be a computerized tabulation plots. So that would be based on, if it's a KT, it's based on calculations with elasticity, or if it's test data, it could be a series of tests on a control material. In that case, it will be specific to the material as well. But this says KT, so that means theoretical, which means it's calculated with elasticity, which means it would be applicable to any material. So here's a material where it would really matter. Gray cast iron, it's used for a lot of heavy shafts because you can make it fairly hard, but it's brittle. In fact, in a lot of cases, it doesn't even have a yield stress quoted. It will tend to fail in tension pretty close to the end of the elastic regime. So the effect of a stress concentrator is particularly bad for a material like cast iron or any other brittle material, because you won't just yield, you'll just fail. You'll end up with fracture. And if you go above or outside of the elastic regime. So if suppose we made this shaft out of gray cast iron, we could look up in a material properties handbook and notice that many cast irons will have an ultimate tensile strength, that means fracture strength, of 180 megapascals. And if we're assuming we don't have any other more severe defect in our shaft, that means we could back out a maximum force if for whatever reason our part geometry conformed to this. We won't necessarily be making a shaft with a groove in it. I mean, just don't machine the groove, right? There may be a groove there needed to, say, hold an O-ring or some other real function in a part. And in fact, an O-ring groove is a great example of a shaft that might have a circumferential groove. So the severity of that, the depth of that groove would be something you'd need to take into account because your max force now has this reducing factor here in terms of what you can apply. You have your area, you have your material property you can tolerate, and rather than saying your max force would just simply be your fracture strength times your area, now we have to cut it down by this KT, and that is a substantial reduction in the amount of force that we could add. So if we were looking at sizing things up, we would have to make a substantial increase in our area and the weight of the part. So this is an example where maybe reconsidering these factors to lower that KT might be the easiest way to lightweight our part and still keep it safe. But that just gives you an example of the power of a stress concentrator in degrading the safety of a material design. These are not small factors. So, and they are inherent to anything that isn't a smooth bar or a sphere, basically. Speaking of which, speaking of being inherent to everything, did you know the end of a part is itself a stress concentrator? A free surface at the end of a part is a big discontinuity. As you go from the middle of a part where you have a uniform stress field out towards the end, the material, the atoms aren't all surrounded by other atoms like they like, and that ends up giving us a stress distribution as we get close to the end that is going to be higher in the middle, lower on the edges, as opposed to uniform straight across like we generally assume. So if we are going to test a material, like we're going to perform a tensile test and we're going to grab it on the ends, we want to make sure that what we call the test gauge is down in the middle and is away from these end effects, which are basically a form of stress concentrators. So we invoke something known as the St. Venanz principle, which says, lucky for us, the effect of an end stress concentrator, or practically any stress concentrator, the effects are going to attenuate the further away we get. So if we're designing a whole part against failure, against yield, we kind of have to assume, the biggest, worst concentrator. But in the case of something that we're pulling on, if we're going to use part of it for a measurement, one of the nice things is we can simply get far enough away from that end discontinuity, the end effect, and get down, like say by going from x1 here to x2, we're going to get to a point where the stress field looks like this. How far away from the end do we have to get? Generally speaking, you have to get as far away from the end as your maximum cross-sectional dimension. So in this case, B is we're wider in B than we are thick in T here. So if we get B distance down from the end, our stress distribution should look like this. And say we wanted to make a strain measurement and we wanted to be able to put our strain gauge, something used for strain measurement, anywhere on the part, and not have it change from say one end to the middle, we'd want to get it at least this far down. So that's St. Venan's principle in action. We can, even if we got stress concentrators, provided we've designed the part to accommodate them so the whole part doesn't yield or break, we can get to a place where stress distribution is still uniform if we get far enough away from the concentrator. And the reason that we zero in on a bar that's held by the ends is that's how a lot of test specimens are made and tested. Things tend to fail in tension, so when we're characterizing properties of a part or a material, we tend to put them into tension and measure the stress strain characteristics. In fact, all of our elastic constants are generally measured that way. So we need to know to get at least as far away as the largest cross-sectional dimension from an end before we do any measurements, because that's how far we have to go to get to that uniform stress field. So that's St. Venanz. Now that would apply even to a through hole. For instance, if we got a certain distance away from that through hole, we'd find that the stress was uniform out here too. So it applies to any discontinuity, but it's particularly useful when determining how far away from an end we have to get before we have a uniform stress for measurements in tension. Hey, and that is it for stress concentrators. You will see these in design exercises and in homeworks. In some cases, you might be told that there is a certain discontinuity, and you'll simply have to know to add that in to what you're designing if you have a design project.